Hello and welcome. One of the last topics we're going to do in hypothesis testing is what are called goodness of fit tests. Okay, so we've seen so many problems, particularly in parameter estimation, where a set of data samples are given and you want to fit it to a particular distribution. You want to, or maybe a frequency table is given, some data is given, and you want to fit it to a particular distribution, right? So you want to imagine, maybe the distribution is Poisson. I do a fit, I find a lambda, and then I see if my actual expected samples are close enough to the observed samples. We've done this quite often, right? We did a gamma fit before, we did a histogram, and we saw if the actual density fits the histogram, etc. We saw all this, but so far we've just visually inspected the expected versus observed and seen if it's a good fit or not, right? We have not actually gone further to look at the goodness of the fit. It turns out there is a statistical process to find goodness of fit. It's very related to hypothesis testing. In fact, there's something called a chi-square test, which is what we will see in this lecture. Okay, so how do you assess goodness of fit? Here is a typical parameter estimation problem, right? So you expect that the distribution of grades in a class from S, A, B, C, D, E, U is going to have this distribution. There is a parameter P in the distribution. The number of people who get C, the fraction of people who get C, the probability of someone getting a C is 1 minus P, and then for B is P by 2, D is P by 8, E is P by 16, U is P by 32, A is P by 4, P by 32. So it's sort of like we are expecting people to have different grades, and in one particular class, I believe there are 810 students in this class. Total is 810. Okay. Out of 810 students who went through for grading, 397 got C, 203 got B, 55 got D, so on. Okay, so you observed this. So from this observation, we know how to go ahead and find P. Okay, in fact, we can do an ML estimate for P. You know that the likelihood is proportional to 1 minus P power 397 times P power 413, and from there you can solve for the ML estimate for P, and that comes out to be 0.51. Okay, so it seems like a reasonable thing to do. We know that this works. Now the question is, how good a fit is this to the observed data, right? So what is the expected count of grades? Okay, if P hat ML were 0.51, the number of S's, what is this number? This number should be 0.51 by 32 times 810. The expected number of S's should be this. So this number will be 0.51 by 4 times 810, and so on, right? So this last number will also be 0.51 by 32 times 810. As per that expectation, I mean, as I have estimated my P, I know the expected distribution, and from there I can find the expected value. So this is the count, and that's observed. So you see the observed numbers are 15 for S, and the expected number is 12.9 as per my fit. The observed number is 97, the expected number is 103.2, 203, 206.6, 397, 396. So these are the numbers I'm getting. The question is this a good enough fit? Maybe you want some statistical analysis method, some p-value, maybe some significance level, maybe to come up with a test to see if this is a reasonable fit or not. Right? This is a typical statistical problem. Okay, so it turns out, if you were to ask a question like, is the above a good enough fit, there is an answer, and that answer, typically one way of answering it is to use something called the chi-squared goodness of fit test. Okay, so how does this work? I'll first describe this test in a general situation, and then apply it in the grade situation and show you how it works. Okay, and then we'll see a couple of modifications of this test. Okay, so the chi-squared goodness of fit test, you have a random variable x. It's discrete. Okay, so first thing we are assuming is this is a discrete random variable. Okay, so it's discrete. We'll see how to deal with continuous a little bit later, but this is a discrete random variable. It takes k values a1 through ak. I'm calling it a1 through ak. This is just to keep it general. It may be different. In the previous case, we saw, if we were looking at grades, it took 7 different values, S, A, B, C, like that. This is a1 through ak. Probability that x equals ai is pi. So this is again a general distribution. So in the previous case, we had some specific values for the probability. In this case, we have a general situation. Okay. It may be that pi is parameterized and you have to find pi from data. That's a different issue. But in general, we start with this point. This is the starting point for goodness of fit test. Okay. And then we take n samples and do this observed versus expected count. Okay. So the data, I mean the possible values are A1, A2 through AK. Okay. The observed values, actually what you saw, the observed counts, right. So this is the possible values for AK. The observed count, number of A1 in the sample end up being this. Okay. So for instance, YK is the number of AK in n samples, like that. Okay. So Y1 will be, number of A1 in n samples. Simple stuff. I'm just writing it down. Okay. Below I write expected value. So n times P1 you can see is clearly the number of A1s I expect in n samples, right. So, as per the distribution is given to you NP1, NP2, NPK. Y's are the actual counts, observed counts, expected counts are below. Okay. Now, I can have a null hypothesis which says the samples are IID according to X, this distribution. The alternative is samples are not IIDX. Okay. So, you see you have a simple null and a composite alternative, and we can try and think of coming up with a test statistic and deciding whether or not this is true. So, a typical hypothesis testing problem. So, it turns out the test statistic of interest here is some sort of a chi-squared statistic. How do you do it? We will call it T. You sum up over I equals 1 to k this number, this fraction. The numerator you have yi minus npi squared. Okay. So, you would do, in this case, if you want to write it down, it will be y1 minus np1 squared by np1 plus y2 minus np2 squared by np2 plus so on, right. So, that is the summation. It turns out this statistic, the distribution of the statistic is approximately chi-squared k minus 1. Okay. Remember the chi-squared distribution, right. I have shown you some plots of that. It is chi-squared with k minus 1 degrees of freedom. Okay. So, this k minus 1, so it is chi-squared with k minus 1 degrees of freedom. So, this degree of freedom is often abbreviated as DOF. So, that is the thing. Okay. And so generally if the fit is very good, you expect this T to be small, right. You can see clearly, yi will be close to NPI, I am squaring it, dividing by NPI, normalizing, etc. So, I expect if the fit were to be really good, then T will be, close to 0, very small, right, positive of course, but close to 0. Okay. So, a very reasonable test is to reject the null hypothesis if T is above some critical value C. Okay. So, based on this and based on the chi-square approximation, you can quickly derive a significance level, which is probability that T is greater than C given H naught, and that will be 1 minus F chi-squared k minus 1 evaluated at the critical value, and this is just the CDF, right, CDF of chi-squared k minus 1. Okay. So, this is the chi-squared goodness of fit test. It is very typical simple test, may not be the greatest of things, but it is commonly used, and you can quickly evaluate the goodness of a fit using the chi-squared goodness of fit test. Okay. So, notice the test statistic again, we have not seen any proof for why this is chi-squared k minus 1. It is a little bit advanced, uses some linear algebra ideas. I will leave you to look it up if you are interested, but this is an important result. Okay. So, once again you see why these things are important, probability, linear algebra, all of these things form the basis of most such results. Of course, you can use the goodness of fit test without understanding the proof, but in some other situation when it fails, you won't know why it failed, right. So, only when you know the proof, you will know maybe this approximation didn't work in this case, right. So, you can go and look at it and do all that if you know the proof. Okay. Of course, that's if you are interested in that. Okay. So, that's the chi-square goodness of fit test. Let us see how it applies for our grades data. Okay. In this grades data, we have 810 samples and k equals 7. So, notice n and k are the only things that play a role there, 810, k equals 7. We have the observed count and the expected count. I put it out separately in 2 tables in the previous slide. I have put it together to show you how it works. And then, so the chi-squared test has degree of freedom k minus 1, 6. We could pick an alpha which is 0.05 and you will get a critical value 3.54. If you compute T, just plug it in, evaluate this, you will get 3.66. And that in fact is greater than C, so you can reject the fit. So, this fit is not good enough at an alpha of 0.05. If you compute the a p-value, in fact instead of C, if you put 3.66, you will get something weaker, much lower than 0.05. So it's not a good enough thing. So how do you find the p-value once again? So if instead of significance level you want to do p-value will be 1 minus f chi squared 6 of 3.66. This will be lesser than 0.05, something smaller. You can compute it. So very low p-value, so you end up rejecting the fit. Okay. So that's the simple application. Grades data. We'll see small modifications to this in the next few lectures, but hopefully this lecture is clear enough. It's a simple test. We didn't see full proofs, but at least the method should be easy enough to use. Thank you very much.